that we have a recorded lecture. Roumen,
yes.
the floor is all yours.
Thank you. So let's go now to the screen. And you'll tell me if you can see my screen well. Can you see it?
Yeah, it's perfect.
Very good. Thanks a lot. Thank you for the introduction, Leo. And thank you everyone who joined this talk. As Leo says, this topic we're doing together for many years. And as Queen says, love of my heart somehow. Today I'm going to talk with you about the microstructure and texture formation of advanced high-strength steel produced via non-conventional technologies. This work, as I said, topic which we like both Leo and I, is something which is not done only by us, but many people involved in the topic. That's why I put the name of large part of them, not all of them, in this list. So the story started around 20 or 18 years ago. And most of my colleagues here that you see in this list, they can find their names, and some of them, they're present here today. They are now professors or responsible engineers in different stages of steel production in big steel companies. Anyway, what triggers our interest to this topic? So everybody knows this famous diagram. I like it especially not only because it's done by our colleague Bruno de Comte, who is not anymore with us, but also because it represents data for advanced strength steels with real samples. It's not the symbolic banana diagram as we say, but they put the real data from real samples which are taken in a standardized samples. And as you see, as you very well known, we have a holy grail here with twip steels, which obviously can be obtained, and nowadays we have this, and even we have steels which are a little bit better than the twip steels, austenitic steels here. But of course, it has its price to get this. Alloying elements, special treatment, some difficulties, and the question which I want to put into touch in this specific talk today is: can we get with the steels that exist nowadays something better, just employing non-standard heat treatment technologies? For example, this is what we have, and the question is, can we move a little bit in this field, a bit upper in this field? And to do this, if I'm going to speak about a non-standard technology, it's very logical to say first what is the standard or classical technologies for heat treatment of steel. In all the cases, we speak about cold-rolled steel, advanced high-strength steels, cold-rolled, low carbon, good weldability to have. And normally those sheets, they're delivered in a cold-rolled condition. I don't say that we don't have hot-rolled steels in this story, but cold-rolled condition are mainly the goal of my topic today. So what we do, we start with a microstructure which are cold-rolled, right per white, deformed grains. Then we start heating them up in the existing devices. Then we have recrystallization. Usually, in most of the cases, we go to the intercritical range when we have partial transformation to austenite, and then purely schematically shown here. This is animation. This austenite is not real austenite. And then after quenching, we end up with a DP structure, or you can end up with the microstructure of trip steel, or you can go and end up with the quenching and partitioning microstructure. All those things, most of you know very, very well. The critical point here, which determines what you end, what structure you end, is in fact what is your preparation stage of the austenite here, which depends on the alloying condition and depends also on the heating rate and the soaking time, because it controls how you distribute the alloying elements. In the classical case, in conventional case, which I'm representing now, the heating and cooling rates usually are in the range from 10 to 20 or 30 degrees per second. If the people from industry, they can correct me nowadays, maybe they can go even up to 50 degrees per second heating rate. And then the soaking times, they stay at a range of few 2-3 minutes to 4-5 minutes, sometimes longer. But this is the classical story, can be found very well documented in the literature. What is a non-conventional, non-standard? If you look at the literature, you can find interesting approaches in which we can apply so-called thermal cycling treatment. Thermal cycling treatment is something which is probably well forgotten. Years ago, it exists mainly oriented to the tool steels or constructional steels for general application, for shafts, for gears. The principle of thermal cycling is that if you start, here is shown schematically with martensitic structure, if you start and go above the AC1, you have multiple nucleation of austenite, and then you form austenite. Then if you cool down, each of those austenite grains is potential nucleation site for formation of martensitic crystals inside, or formation of different non-equilibrium or equilibrium perlitic structures here. And if you repeat the cycle again, nucleations sites are again inside this, in between the grains or inside. And then again you have austenite, which is with finer grains, and then you can make this many, many, many times. And finally, when you select one appropriate austenite grain size, you can go to the final quenching step, and then you end with your final microstructure refined, and then you can have better toughness, better strengthened material. Is it work? If you look at the literature, you will find out that actually it works pretty well. This is a paper from Pavel Kraska and Geert Dubsk, which is from a pretty long time ago, as I said, 1979, and they show for the same chemical composition here, this steel with 0.4, they show how the austenite grain size changes depending. They heat up and quench depending on the number of thermal cycles, heating and quenching in a fully austenitic range. So then they etch the austenite grains, and heating rate is around 100 per second, which is also pretty high here. As you see, depending on number of cycles from one cycle, this is the distribution of the average grain diameter, and here is the quench temperature. The grain size of austenite depends on the temperature to which you heat up, also obvious, and then depends on the number of cycles. And then even after the first cycle, you could have significant refining of the grains, if you do not exceed some austenitization temperature. Obviously, if you do this, and this is still B here, and which has slightly different composition, but very slightly different composition, 0.8. This is 2 steel actually, and chromium, and then effect is even probably better pronounced. And here you can trace the influence of the temperature in which you reheat. This is 1050, and this is 850 degrees. Obviously, you have 2 in your hands, which you can use, and you can try to get better properties if you prepare your austenite before the transformation in that way. Another non-conventional technology to which we work from, as I said, a pretty long time ago, is ultra-fast heating. Ultra-fast heating, or ultra-rapid heating, or ultra-short annealing, or flash heating also, it exists with many different names, is nothing else than heating up very fast to the temperature range between AC1 and AC3 or above AC3 temperature, which AC3 temperature, AC1 temperature, which are for this specific heating rate, because everybody knows that those temperatures, they depend on the chemical composition, but also on the heating rate. Or you can, and then if you go there without isothermal soaking, start cooling, then you can have different type of cooling. So you prepare your austenite at that stage before transformation. Yeah. This is something which is also studied quite a lot in the years, and I will put here 2 specific points. One point is how this phenomenon is projected in low carbon and IF steels, nearly pure iron. As you can see here, this is the work of Michael Ferry. This is the recrystallite fraction. And this is the start of the recrystallization, end of the recrystallization. Those are not kinetic curves, but they're linked with the temperature. They shows the dependence on the temperature of the recrystallite fraction from the temperature. As you see here, that with increase of the heating rate, recrystallization is suppressed. It starts at high temperatures and process a little bit slower than in the case that you have lower heating rates. Yeah. This immediately reflects to the average grain diameter, which is obtained with those heating rates. You see here how change of the heating rate, and here we went up to 2000 Celsius per second. You have around 1000, you have kind of stabilization and very fine grain, which is nearly 4 times smaller in knife steels. This is something which is observed. Additionally, carbon content shows, even small carbon content shows influence on the grain size and the behavior. And of course, if you have changes in the grain size, normally you expect to have changes also in the mechanical properties of this steel. And as you can see here, for example, if you if you have a small grain diameters here, which can be obtained with different heating rates, 50 per second and 250 Kelvin per second, obviously the contribution to the yield strength is visible in this work. This is the work of Valérie Massardière, Damien Fabrecht from University of Lyon years ago published. So the question is now, this is only for nearly pure iron, only based on the diffusion of iron atoms in the. So what will happen if you have something which participates, another player, like carbon here, and then I a little bit to move aside. When this story, I have seen this story with the works of Anna Carmen in the beginning, so this something is not very clear here. I was a little bit not believer. And then we decided to check this on a trip steel with Leo. And then the story started. We made this relatively simple experiment. Interrupted heating. You take a sample, you heat up the sample with different heating rates, and then you quench. You quench, and you quench, and you quench in different temperatures, and then you have like a snapshot of the microstructure and the properties. You don't have isothermal soaking time. You get only the beginning of transformation, and then you get it. So we made this test for many different heating rates, from 10 to even 7,000 UN. And then we trace how the hardness of those samples changes. Of course, I'm not going to show all those things here. The steel in which we did this is classical steel. At that time was considered as a very good example for trip-assisted steel. For the moment, we only make quenching just to trace the phase transformations here. And if you see for the 10 degree per second with the empty balls here, with initial structure here was martensite, tempered martensite and ferrite, 50-50. And after cold rolling, the hardness was 350. If you start heating and quenching from different temperatures, even below S3, you can see first slight increase of the hardness, which are effect of aging. And then when the recovery and recrystallization start, the hardness decreases. Here you have full recrystallization. Then the phase transformation point is reached for this heating rate, and then formation of martensite starts in the structure. And if I continue heating, it will go to some level here, for example. So we stop here because we know now that we have recrystallization. When you get this, you make this experiment exactly on the same material with 3,000 per second or even 7,000 per second. Obviously, the stage of recrystallization, first part here, is missing. You don't have any changes. We did not observe any changes in the microstructure, in the hardness. And immediately the hardness started increasing after the point very much shifted AC1, AC3 point, started increasing without recrystallization, without decreasing before that. Looking at the microstructure, the effect is very well demonstrated. So this is with the 10 degrees per second from temperature, which was here, 800 degrees. It corresponds to this point here. 10 degrees per second with 50 degrees per second. If you go very fast, you see already formation of those white zones, which are before that was austenite, now they're martensite, yeah, and the ferrite remains. And if you go to the high heating rates, this is what appears. So those things are pretty well known for most of the colleagues who are here, who also participate in this type of experiments. Yeah. So obviously, one of the effects that you have seen is refining of the grains. And then if you make a map of the grain size, whatever grain size means, in this case, what I plot is the average calculated grain diameter derived by EBSD, which means that it contains not only ferrite grains, but also the martensitic grain structure, which we derive with the resolution of the EBSD for the high angle grain boundaries. So this is, which means that it can take also blocks inside as a grain. And then if you plot this, if you make this plot, you end up with this distribution of the grain sizes here, which is very nice, shows very nice tendency. And what is very important, and luckily it's very important, that we have one quite safe zone here in which the grains are refined without necessity to go to extremely high heating rates above 1000. Here is 1000 is here, and then you have here 2000, 3, 4, yeah, 7000. There's one specific point, one special element here, which normally you can ask me, why does it come from? It's around 140 degrees. And this specific point is when you have a quench delay. Quench delay, I call the time between the peak temperature when it is reached and the beginning of the cooling. This quench delay we had because our samples here were heat treated in the salt bath. So we have a robot which needs around 8 seconds to move from the salt bath to transfer the sample from one salt bath to another salt bath for quenching. That's the story. As you see, the effect can be destroyed immediately by this quench delay, which is very important point. Good. So let's see now those non-conventional things, how they can be applied in practice, or can they be applied in practice? What we do nowadays in the practice with a conventional treatment. Conventional treatment, the stills is done continuously in lines. You have this story here on coiling, welding, then it goes to different heating zones here. Then you could have overaging. Those blocks, they can be controlled. And finally, you end up with the heat-treated sample here. This is done with quite complex devices here, and the entire cycle from which one point passes to the heat treatment cycle, which means from the point from heating here, the heating zone until the quench zone is around 8 minutes, which is pretty short time here for. And this in these devices, you can have heating rates, as I said, 10, 20, 30, 50 maximum, depending. How they are heated? What is the heating principle here? For heating principle, here we use radiant tubes. With the gases, they heat, and this is the tubes here, and the strip goes in between them. So radiant tubes, they use hydrocarbon gases. And they have heat transfer from the tube to the sample. Actually, you heat something, then you transfer the heat, and then the heat should go in the sample, and then to increase and to reach the temperature. It is obviously delayed. And the logical question is why we don't use a method which can generate the heat directly. In most of our experiments, we use direct Joule heating. We simply pass current through the sample, and we had one safe zone, like in Glibel, which you can have homogeneous temperature distribution, and so on and so on. Industrially, this is not possible, but industrially, it's very possible to use transverse induction heating. Schematically, here you can see this transverse induction heating system, which, yes, purely schematic, they're much more complex, which generates the heat inside the sample. Of course, obviously, even here you see that there's a temperature gradients. And then, of course, this question can rise after that if you start discussing the technological difficulties. And people from industry, they know this, and there's a way to avoid somehow this, or to minimize this. What are the advantages? You have extreme thermal efficiency above 75%. You generate the heat inside. You don't have transfer from outside to inside. Greenhouse gas emissions, depending from where you get your electricity, could be zero. I don't say that they're zero, but depending on the way how you can get your electricity. 50 to 20% less floor space. Years ago, in 2001, I have seen presentation in recrystallization grain growth from colleagues from Japan. They say that they shorten the line from 64 to 16 meters, right? Imposing short annealing approach. And then, of course, the heat treatment is much faster with the high heating rates. Just the total process, the total productivity of the line can be increased. So those are many, many advantages. Another question for me was, is this topic new or not? And some time ago, I made one relatively good study of what is published. You see, those are the number of papers of ultra-fast heating of steels or rapid annealing. Only I use those keywords here. And this is until 2021. And then only in the last 3 years, we have around 1,000 papers more. And this is what is put after that. So you see, just in 3 years' time. It means that this topic is hot topic. This topic is something that people are interested more and more, and they really go there because of the advantages that I say. Results about thermal cycling is not so well pronounced. They are only around 2050 results I found. Most of them are in Russian language, and they in this period 60 to 2023, and only 150 in English I found, which means that this topic is probably or forgotten here somehow, or not well studied, or not yet with the eye for application there. So if you'd like to see more about that, we can take a look on those recent reviews here of those colleagues. So based on what I said, I want to put several questions here now. It's important to know what is the influence of the high and very high heating rates on the microstructure properties of advanced high strength steels. We have seen grain refinement, but how it works, is it only the reason to get, if it gives good properties after that? What is the potential of ultra-rapid heating and thermal cycling to improve the microstructure properties? How much we can go, how far we can go? What is the influence of those approaches on the crystallographic textures? It was almost never discussed, this topic. Which mechanisms control the microstructure changes and how they can be controlled? How many things we can use here in this story? Logical question, is it green technology? Can be developed to the industrial technology? I can put more questions here, but I leave this up to you to ask, and then to ask them and to announce them to the public and try to find answer maybe. To try to answer some of the questions, I will show you briefly only part of the results on those type of steels that we have seen. Apologies for this unclear printing here, that something happens with Arial font on my computer. Those are steels which are with composition of DP steels, steel which we use as a trip-assisted steel, and steel which we use as a quenching and partitioning steel, and most of them they have AC1, AC3 in the range between 760 and 900 degrees. And we did experiments with different microstructures before ultra-fast heating, cold rolled to different reductions. It's important to control the balance between recrystallization and phase transformations. And it's important if the microstructure is peroite and ferrite cold rolled, or it is ferrite and tempered martensite. It has really importance. The experiments were done, all of them, on heat treatment devices, dilatometer, glibble, or this homemade glibble, which we don't have it anymore. And of course, we use all our range of characterization techniques here, mainly linked with the crystallographic analysis, and we study mechanical properties in the classical ways. And this is work which is done from all those people on the second page today. My colleagues, PhD colleagues, guided from us here with Leo, and also with Spiros, also in Greece, and so on and so on. One example for the trip steel, which is gives answer to many of the questions. So this composition was with initial structure of ferrite and peroite, cold rolled 70%, and then the AC1, AC3 temperature were in this range. As I said, here you can see the microstructure. From we made characterization on the samples we made a treatment on glibble device. Samples were with specific geometry, which allows to have a homogeneous heat treatment zone in the center around 8 millimeters. And then the gauge length here is 8 millimeters for those samples, which make us thinking that we could have reasonable comparable results for the properties. Orientation of the sample was with a long axis along the sample rolling, the sheet rolling direction. And we did this story. And we put the cycles in the following order. So we have, first we have ultra-rapid heating with this scheme here, where the heating rate was 500 Celsius per second. This is part of the PhD of Eliseo Hernandez Duran. And we can see the entire paper here. 0.3 seconds approximately is the circuit that you just switch and go to cooling mode here. And the AC3 temperature for the heating rate with 500 degrees per second is somewhere here. So we went to 925, around 25, 30 degrees above this one, because with the slow heating rate, AC3 temperature is lower. And then we went and made our tampering. We had also samples which are directly quenched only to see the traces of the pre-transformation state of austenite. We had also conventional treatment with 10 degrees per second. And here, this is the AC3 temperature for around 850, and we went to 885. So obviously you have difference in the temperature. We keep here 180 seconds for homogenization. This is kind of classical cycle. And then we went for our tempering here. This is the second, which I call conventional annealing, CA. And this is the thermocycling, which imposed 3 cycles after quenching after the first cycle. And then 3 times you have this 3 minutes here, then make 3 times again. And then you end up with some microstructure with our tempering at the end. Those are 3 things. When you make this type of treatment, first thing that we're going to see is what? Of course, austenite grain size, because we want to see if all those exercises which we do, how do they influence the austenite grain size? And this is reconstructed inverse pole figure maps and normal direction inverse pole figure maps of prior austenite grain size. We use here the software of Oxford, TSL software for reconstruction using KS, Kudryavon-Sachs reconstruction algorithm here. And as you see in a conventional annealing, this is the structure. Thermocycling gives already remarkable refining, and ultra-rapid heating gives also refining. Here I plot the average prior austenite grain size, and here is the average block length here. So this is the link between the block length of the notice that and the prior austenite grain size. And here is what we have here as a ultra-rapid heating and thermocycling, practically the same, and conventional annealing. In fact, if you there's one model which is Galindo and Nava say that the yield strength contribution of the diameter of the block size here linked to the prior austenite grain size is the following. So if you have small grains, this around 300 megapascals we can get for those grain sizes here only by the refining of austenite, which is not really very big. So then the question is if this refining is enough to have better strength in the material. After austempering, the structure looks like that. You see here the retained austenite, 14%, 15, 14. Definitely, there's no significant difference in the retained austenite fraction. Bainite differs a little bit more, bainitic structure, bainitic constituent stays a little bit more, and ferrite varies also. Please mention that ferrite fraction increases for the thermocyclic and for ultra-rapid heating. Have in mind that thermocyclic is also made with a 3 times higher heating rate than the conventional annealing. Mention please also that here in this microstructure, ACM microstructure, with ultra-rapid heating, we have here zones in which we have cementite, which is non-dissolved. Such zones of cementite, they cannot be found here, or very small amount, but here they do not exist practically. Here also they do not exist, but here is some zones which are definitely like that. And also something which is very important in ultra-rapid heating, you have zones in which you have ferrite. Although the temperatures are higher here, but you have zones with ferrite inside. Much more than in the other case. If I make global view, because now could say, okay, you have selected this zone with ferrite. If I make a much lower magnification, and this is for conventional annealing, practically you don't see the black points with ferrite, or only 1. Or here 2. If you have thermal cycling, then you have those zones of ferrite which are formed a little bit more randomly, but they're very small. And if you have ultra fast heating, the zones of ferrite is much more, and the carbides are still there. Carbides are very well pronounced here. Some of them, they are non-dissolved, the cementite lamellas. Some of them, they're spheroidized cementite lamellas. The question is, what is the influence of those non-dissolved cementites on the microstructure? Here you can see part in which we have interface between ferrite, some zone with a very specific microstructure here, in which we have retained austenite and martensite. And we know that this is retained austenite and martensite because when we made after that on lamella, on such zone, when we make TM, we can see clearly that this zone is retained austenite. And then in TM, we made analysis of the distribution of the alloying elements in this retained in this austenite here. Here you see this small part. If you look carefully, you can recognize immediately this small part here. This part is here, this part. Yeah. And then we made this analysis here, and you can trace the distribution of the elements. Manganese with green and silicon with red. Nothing unusual. Silicon and manganese, they go in the opposite direction. But the fact is that in this zone you have a significant difference in the content of manganese and silicon. What does it mean? It means that you have in this small scale possibility for formation of different type of microstructure in a very small scale, because the cooling rate in this zone is exactly the same, but the composition of your austenite is different. And then, of course, if you have martensite in surrounding of ferrite, you have additional effect which can strengthen the microstructure. And this additional effect is associated with the fact that this martensite generates, due to the changes, the volume changes, generates dislocation structure. What you see here is a TM bright field image, in which you as quench sample, in which you have martensite and ferrite. You can see clearly the dislocations here, dislocation network here. This map is kernel average misorientation map from 0 to 4 degrees, calculated for the, as far as you can remember, to the fifth nearest neighbor. Here you can, practically it's exactly the same zone. Here you can see ferrite, martensite, and you see the kernel map here, the local misorientation scale. Obviously, this combination of martensite and ferrite gives this strengthening effect of your ferrite there. And then what, if we make a short summary now, what we have? We have heterogeneous microstructure. We have heterogeneous with respect to the chemical composition. Microstructure in which you have additional strengthening of the hard phase. And we have microstructure in which we have carbides non-dissolved, which gives changes in the chemical composition of austenite, which means that you have difference in the transformation products, which means also that your martensite probably which forms is with a lower carbon content than can be as a carbon content in the conventional annealing, when they have time, carbon has time to go, and the alloying element has time to homogenize. Yeah. And you have different kinetic of transformation. If I put this schematically here, I have initial microstructure of cold road structure here. I have after conventional annealing the structure here, and I have the structure after ultrafast heating. You see, ultrafast heating structure has kind of pattern, which still keeps the pattern of perlite structural constituents distributed. If I magnify this zone, you see the story that I showed you before. Ferrite, non-dissolved, and zones of martensite here. And if we put the previous discussions about the distribution of the elements, we can end up to the following story. Purely schematically here, I draw the TTT diagrams, or CST diagrams, or TTT diagrams in this case, for coarse prior austenite grain size, and if you have fine prior austenite grain size, they will differ. The kinetics will be different for the different grain sizes, and also MS temperature will be slightly different. This so-called, effect of the grain size of MS temperature. If you have heterogeneous microstructure with a low alloyed austenite, it will transform easily with diffusional or mixed mechanism or martensite than the highly alloyed martensite, which has high amount of carbon and manganese, the effects that we observe in some zones. This explains this mixture of the microstructure that we observe, and probably it will influence the properties. But before going to the properties, I want to go to the crystallographic textures. Crystallographic textures, here, this is the measurement of those three crystallographic textures. Left-hand side, you see the classical 5 to 45 section for BCC metals here, just to help you to read better the orientation distribution functions. Orientation distribution functions are taken based on the enough large scans to be statistically representative. This is the orientation distribution function showing the texture of the cold road material, cold road steel with a maximum of 5.2 intensity. Nothing unusual. Yeah, ND fiber, RD fiber with this specific curvature here. If we have Conventional annealing, conventional annealing, and then the texture, as you see, goes and changes to typical recrystallization type of texture. Why I say typical? Because if you open the books and old papers, you'll see that for this type of steel, we have one kind of specific curvature here that we discover in ND fibers here, which is this a paper of, I think, Leo and Dick van der Schuren years ago. And I say Leo will help me after that, which you have this typical curvature, which is kind of indication for recrystallization texture, and is linked with the specific grain growth of the components. Very interesting is that the multiple transformation in thermal cycling, the texture is extremely weak. Actually, this texture is 1.6 is the maximum intensity, and it resolves almost the rotated cube here, small components, small intensity here, around 1.6. One is the random texture, and even gauze can be found with intensity around 1 here, a little bit. Whereas the ultra rapid heating texture, this one and that one, if I change the colors of those to make this what is here, with this one, they probably, you cannot recognize what is what. They definitely resembles the cold roll texture, only the intensity is smaller. Why smaller? Because practically you multiply this by 24 orientations, and then they spread around those intensities, which means that this ultra-fast heating gives you some possibility by heating rate to have, to some extent, texture control. Changing the heating rate, changing the cycles, you can control this somehow. What is the reason for why this the cold roll texture appears? Very easy, you can see this if you separate the elements in the structure. Separating the elements in the structure is possible by going to your EBSD scan, and then you make one good kernel map, and then you select the zones with a little bit higher kernel average Mueller orientation above, let's say, 1.5 degrees. And those zones, they correspond very well to a part of the microstructure which is non-recrystallized. And then this is the texture of this non-recrystallized. See this thing with a very high intensity because the grains are small. See this one. Practically they are the same. To check if our hypothesis for suppressing the recrystallization is true, we try some modeling exercise. This work was done by Tuan. I don't know if he's here and listening, but he made this exercise. What he did, he took the initial cold roll texture here, and then he applied the transformation rules, KS, and he calculated the texture of austenite, imposing after transformation also one recrystallization model, which gives preferential grain growth of specific orientations. He did this the same for ultra fast heating, but said, okay, now we are not going to have this recrystallization because we suppose there is no recrystallization. And he stopped this. And then he made this for thermal cycling, again, imposing this several times. And then he calculated back from this thing, he calculated back his transformation textures. This is all what you see here is calculation. So, and if you compare this with the measured textures, this is the results. As you see, the cube texture here, which is good indication for recrystallization austenite, is missing. Yeah, and you don't here, you see? And whereas here it is present in this case. Is it true? Yes. From here we went to here by modeling, assuming that there is no recrystallization. Luckily, dealing with trip steels, you still have austenite there, and then we can still check the orientation of austenite. And if you check the orientation of austenite, you end up with this nice story. Here I plot the three ODFs of the austenite, and here you have conventional, and immediately you can see the indication for recrystallization component of austenite with a little bit small gauze here. Here is missing, even gauze is missing. This is a real measurement. And here again you have this one plus gauze. To get gauze texture component in this story with transformation, you should have. This is the clear indicator for transformation of recrystallized austenite, at least for what we know until now. This is the story with the texture and microstructures in this steel. what about the properties? What we gain after those exercises in this deep analysis here? Here you see the three representative tensor curves, tensor test curves: conventional annealing black, thermocycling, and ultra-rapid heating. There's no significant difference in the tensor curves in conventional annealing thermocycling. And this is, in fact, only caused by the effect of the grain size. And to be honest, I was very happy to see this because it fits very well with this model prediction. This small 30 megapascals that we get. And here they're practically, but yeah, this little bit better than the conventional annealing story. Ultra-rapid heating has significant contribution to the deformation, and very good characteristics of this is to calculate the absorbed energy. And we calculated the area under the curve just to have an idea about this difference. As you see, you have only 6% contribution difference between those areas, but here you have around 50% contribution to the absorbed energy in this steel. And obviously, here we have the effect of this is due to these complex acting mechanisms. This is about trip steel. I went here in details. Now I'm run a little bit more to the other type of steels. We did these experiments on DP structures, and then effect on the mechanical properties is again the same. After heating with 10 degrees per second, 500 per second, and 1000 per second. And then here we are at the small standard size samples. There's no possible overestimation of elongations or such things. And we did this also on different, slightly different grade, again, which we have different initial microstructures, different range. Ferrite and tempered martensite, and ferrite and perlite with high heating rates. You see the differences here. And we did this in low heating rates, and again, you see some differences here, which means that the initial microstructure also has significant influence to it. It can be used to control. Is it logical? I think yes, because initial microstructure shows you the distribution of the element which will diffuse at high temperature and will form your austenite. And because here the time is very important, this is from critical importance also. What kind of initial microstructure? Practically, it means that if you'd like to have good results, maybe you should start your heat treatment with already done heat treatment before. A few examples for quenching and partitioning. QMP steels with this composition here, hot rolled, carbides, ultra-fast annealing, glebo, those things we do. Tensile tests with small standard size samples. And again, the cycles that are done on this QMP was like that: ultra fast, then quenching, then partitioning here. And then here you have two different heating rates, 1500. Those are fully accessible in most of the devices. Classical, conventional 110 degrees per second, 5-minute soaking, quenching and partitioning. 10 degrees per second, no soaking, quenching and partitioning. And the results here are also very interesting. Looking only at the microstructure of QMP steel, you see that even without soaking, with 10 degrees per second, you can get here pretty good grain refinement. In the other cases, it's even not so well pronounced. And here is the distribution of the fresh martensite, and here you have the retained austenite. Black is fresh martensite, tempered martensite is brighter, and this image quality map with inverse pole figure map. And if you see all those, here is shown, down is shown the soaking time and the heating rate, and obviously you can see here the refining effect in those cases. Not so well pronounced very much. Exactly the same story with the textures. This is the examples. Those are pure examples from the literature, recrystallization texture and deformation. This is deformation texture. This is our cold rolled recrystallization clearly here. Almost the same, 45 minutes. Sorry, gentlemen, I'm approaching end. And here is after 500, and here weakening of the texture. So those things, if I put here now the grain size after QMP, again, they follow the rules. It means that we have good repeatability of our results. And logical question here is about what will happen if I go to fully austenitic range. All my examples here was in intermediate. Very sensitive to the temperature and the time in fully austenitic range. Here you see 1000 degree, we get in fully austenitic range, 1053, the sorting time is again 0.3, or less than 1 second. Yeah, and 1000. Immediately the grain growth starts like a spring, which is like to go. And oh no, this is something which should not. If I put those data now from where we have been in the beginning, our goal was to see how we can move those things here. This is the steel with QMP. It can be shifted in this range. This is the steel which is the dippy steel. This is one of the trip steels, and this is another of the trip steels. So practically, we can reach this story. Is it possible this to be rescaled? People tried to do this from years. Known things, RFCS project from 2000 already, which stays somewhere hidden, or I don't know. Works of Penty-Carolinen are very interesting, but they did not have enough power for inductor to make quenching, or at least they never published this. They do this for high heating rate tempering, which has excellent results also, but a different topic. This is how it looks like. Very popular are the works of Gary Kowa Jr. He, a little bit later, we start this in 2002, he did this in 2010 already, after some works of Suresh Babu and Boyan Alexandrov from Ohio State University. He made design of this device in which he uses induction heating. First was flame, and then he switched to induction heating, and then this is schematic. It's not how exactly it works like, but he makes excellent story with increase the strength and ductility of the material. He applied this practically, and here you can see example for grade 60, a part for a car, which is made of grade 60, and to survive the test, it should be like that. But if you make from the same steel grade and make flash heating, goes to these dimensions. And just to show you. Of course, nowadays, people work on this. We're not the first one, but somehow this work goes here and there a little bit hidden, I think. Everyone is digging, trying to get on the market with something. So I hope that at least after this talk, we'll start working together, more together, probably can get better stuff. This you can, for example, buy such from the FireCLS group. This is demo unit. Again, this is purely schematic transverse inductor, which allows you to go with up to 300 per second, up to 1200 degrees. Yeah, that's very remarkable. And the last question for today, and then I really leave. Ultra-fast heating, is it ecological? Is it clean technology? Thanks to Eliseo, he made this analysis of this work here, which is a European project. Yeah, you see, if you want to heat up from 20 to 1150 degrees still, 2000 kilotons still per year, you need energy just to reach this temperature around 40 gigawatt hour. This you can get with furnace gas, which has efficiency of 0.6, with a power consumption of 67 gigawatt per hour. With induction furnace with efficiency 0.75, and as far as I know, now the efficiency is even higher, you need only 53 gigawatt per hour, which is around 70 kilowatt hour per ton energy saving. Gas emissions. Practically, if you go for carbon gases here, you will have this emission of furnace gas here and nitrogen. If you go for electricity, and which is really green electricity, then you have to go and practically you have only this CO2. That's practically zero, very small, 11 gram per kilowatt hour compared with it. Of course, electricity doesn't come only from the sources. We should be realistic. Yeah? It comes also from sources of nuclear energy, or also we have different burnt coals also, and so on and so on. So, however, looking in the green direction, in the direction of the windmills, and this, you have to think about that. And then with this summary, I want to answer all the questions that I put. Ultra-rapid heating activates all strengthening mechanisms, starting with significant refinement of prior state grains. It distributes phases with different properties on a very small scale. You have incomplete carbide dissolution, which gives, first, pinning effect on austenite grains. Second, the difference in the chemical compositions. Then you have less carbon for partitioning, for example. You make a softer but more ductile martensite. We have this cyclic heating refines the prior austenite grains, but also it's not as effective as ultra rapid heating, because only here the effect is of the you lose the effect that I mentioned before for heterogeneity of microstructures. Only grain size effect plays here. The texture after cycling heating is weaker. I don't know if it is good or bad, but but with rapid heating you can inherit the previous texture. And yes, you have possibilities for industrial application. There's potential for clean technology, low CO2 emissions. Excuse me, here my C dropped. You see I have problems with C here. And with this, I would like to thank you for the patience to listen to my enthusiastic talk, and I'm very happy to hear your questions. Thank you.